All right, here we go. Okay, so I want to wrap up. This is it for this unit. Unit 3, we're done after today. I've got the review assignment is already up there. I'm going to give you tomorrow to work in class. We'll do an in-class review on Thursday, and then I'm hoping to do the test on Friday. Okay, so we got a lot to do this week. So transformations, right? What did we say? Let's review a little bit. It's been a long weekend. So we said on Friday that there are 3 things we can do to transform functions. We talked about 2 of them. You know, we had these 3 numbers, these 3 parameters, A, H, and K. Remember, H was the horizontal translation. That was the number that we subtract from X inside the function. K was the vertical translation. You know, how far we slide the graph vertically, that's the number that we add outside of the function. And then the one we haven't really talked about yet is A, which is the vertical dilation factor, and that's the number that we're multiplying by the function. So it's the number out front, the coefficient, the number that's out front that's being multiplied by the function. That's the one that we want to investigate now. So let's take a look and see what the effect of multiplying a function by a number is. So I've got this Desmos document here. I've got this basic, P of x, my parent graph is just absolute value of x, just a V-shaped graph with a vertex at the origin. Now I want to know what happens if I replace that, or I'm going to graph along next to that, I'm going to graph f of x, which is a times the absolute value function. Well, right now a is 1, so it hasn't changed anything, right? But I want to know what's going to happen if I make a something different. Okay? Well, first of all, let's just see what happens if I make it 2. What'd it do? Okay, so yeah, I mean, you could look at that maybe in 2 ways. You could probably describe that what just happened in 2 ways. It sort of looks like I squeezed it in from the sides, so I horizontally compressed it, or I vertically stretched it. But those are both not accurate. Only one of those is actually what happened. Now you can tell which one it is if I put those points back into the graph, the red points on the red graph. They start off exactly lined up with the green points on the parent graph. But watch what happens as I drag a from 1 up to 2. So I'm going to start multiplying the function by bigger and bigger numbers until I end at 2. What did it do?
It is added to the vertical.
Did it? Yeah, so which one was it? Did it stretch it vertically or did it compress it horizontally? Stretched it vertically, didn't it? Right? And again, watch that again. Those points, you'll notice, they didn't move horizontally at all. They only got stretched up vertically. Right? They did not move. They didn't get squeezed in. They got stretched up, didn't they? Okay, so that gives us our answer. When we multiply a function by a number, it stretches it by that amount. And look at the ordered pairs. They tell a story here. Like with my normal green parent graph, if I started at the origin and I wanted to tell an ant how to get to another point on my green parent graph, there's a bunch of different things I could tell him. I could say walk 1 to the right and 1 up, right? I could say walk 2 to the right and then walk up vertically 2. Walk 4 to the right and walk up vertically 4. But when I multiply the function by 2, it changes those instructions. Now I would say walk 1 to the right and walk up twice as far as I normally do, right? Walk up 2 times 1, so I walk up 2. Walk 2 to the right and walk up, my 2 times 2 is 4. Walk 4 to the right and walk up vertically 4 times 2, so walk up 8. What would happen if I multiplied this function by 3? What would it do? Instead of multiplying by 2, what's going to happen to this thing if I multiply by 3? It's going to stretch it even more, right? Now I'm going to stretch it so it's 3 times as tall as it was originally, right? So look at this. Okay, again, we'll start at 1. And if I drag this thing all the way up until I'm multiplying by 3, look what it did. See, now it dragged all those heights up so they're 3 times as high as they were originally. Instead of going 1 to the right and up 1, I'd tell the ant go 1 to the right and now go up 3. Go 2 to the right. Instead of going up 2, you got to go up 6. From the vertex, if I go 4 to the right, now I've got to go up 12 to get to the function. Okay, give me thumbs. Does that make sense? Okay, so what would happen, do you suppose, if I changed a to a fraction that's less than 1, like 1/2? Ah, okay, that's going to squish things vertically then, right? So let's watch that. Okay, so we'll start at 1. And let's drag a down to 1/2. Wow, look what it did. That's exactly what it did, isn't it? So now if I go 4 to the right from the vertex, instead of going up 4 to get to my next point, I only go up half that far. Okay, everybody see that? So how could we summarize all that stuff? Well, when I multiply a function times a number that's greater than 1, if a is greater than 1, then I'm going to stretch it by that factor. Right? Factors are things that I multiply. So I'm going to stretch it by a factor of 3 means I'm going to multiply all the heights by 3. It gets 3 times as tall. If I multiply it by a value of a that's less than 1, like 1/2, then I end up compressing it by that factor. It gets squished or compressed. Okay, give me thumbs. Make sense? All right, make another prediction for me here. What's going to happen if I make a negative? What do you think it's going to do? Like, what happens if I make the value of a -1? What do you think is going to happen?
It's going to split it.
Ah, okay, let's try that. Yeah, look what it did. Okay, and now it opens downward instead. What if I make it -2? What's it going to do? It's going to the negative part's going to flip it or reflect it. What's the 2 part going to do? Is it going to stretch it or compress it? Stretch it, yeah, absolutely. Okay, and look, we can see that, right? Now, look at those numbers. And we can think about it the same way. Instead of telling the ant to go, if he starts at the vertex and he wants to go to that point up there, let's say, he'd go right 4 and up 4. Now he's going to go right 4 and he's going to go up 4 times a, which is -2. So he's going to go right 4 and up -8. How do you go up -8? What's that mean? Yeah, going up -8 means going down 8, doesn't it? So I go right 4 and down 8, and there I am. Okay, make sense? Yeah. All right. So the negative part of a just ends up reflecting the function so it opens the other direction, so it opens down. Okay? All right, so then now we can put all this stuff together, and we can even make it simpler. So we got these 3 numbers, right? We said h is the horizontal translation, k is the vertical shift or translation, and a tells us how much we stretch the function. So if we want to graph these functions, we can be really tricky about this, right? We know that normally all the functions we work with always start off with the vertex where, do you suppose, in the parent graph? This 0, 0 at the origin, right? That's the way it was for our absolute value function. The point of the v, or the vertex, was at the origin. That's the way it's going to be in a couple units when we deal with quadratic functions. The vertex of the U-shaped parabola, the point of the parabola, is going to be at 0, 0. All the functions we work with, the vertex is always going to end up starting at 0, 0. So we can be tricky about this. We can just shift these, we can shift the graph one step at a time, or we can do this. We can say, I know that if the vertex is starting off at 0, 0, and I'm going to do these 2 things. I'm going to shift the vertex horizontally by h units. Well, then if the vertex starts off with an x-coordinate of 0, what's its x-coordinate going to be after I shift it horizontally h? Isn't it just going to be h? Right? The vertex started at the origin, so its x location was at 0. If I slide this thing horizontally by h, doesn't the x coordinate just end up being whatever h is? Make sense? If h is positive 3, then we slid it to the right by 3, and the x coordinate of the vertex is going to be 3. If h is negative 2, we slide it left by 2, and the x coordinate of the vertex ends up being negative 2. Give me thumbs. Does that make sense? Okay, using the same logic, if we're going to slide the whole graph vertically a distance of k, and the y-coordinate of the vertex starts off at 0, doesn't it just end up at k?
Yep.
Ah, okay. So then h and k, we don't even have to think about them as translations. We can just think about them as the coordinates of the vertex of our graph. And we can do it in one step instead of two. Okay? And then to get the rest of the graph, we're just going to use a t-table, and we'll go through a couple examples. Before we jump into that, though, I want you guys to practice looking at a function and determining what are the values of a, h, and k. So we'll go through a couple practice problems here. Now I want you to think about, so I'm giving you f of x. F of x is this function right here, 3 times the absolute value of x minus 2 plus 1. Okay, first of all, what is the parent function here? If I were to erase all the numbers and make this as boring as possible, what kind of function would we end up getting? See what I'm saying? Like if I erased all the numbers that are spicing this up, doesn't that mean I'm going to erase that 3? I'm going to erase that 2 that's being subtracted from x. I'm going to erase that 1 that's being added on the end. And what am I left with? Just the absolute value of x, right? Okay, do you see my point there? So my parent graph is just an absolute value function. Show me with your hands again, what's the shape of an absolute value graph? It's a V. Good. So we know that tells us what the shape of this thing is going to be. It's going to be a V. Okay, what's the value of A? Show me with your fingers, everybody. What's the value of A? That's, remember, and what is A? A is the number that's being multiplied by the function out front. Whoops. So what's A? Yeah, it's 3. It's right there. That's the number that's being multiplied by my absolute value function is 3. What's the value of H? And be careful. Is it negative 2? No, it's 2. It's 2. Because remember our trick. It's always going to be the opposite of whatever that operation is, right? So H is actually, in this case, positive 2. And what's K? 1. All right. Go to the boards real quick. Go to the boards. Okay, all you're going to do each time, what do you need? Yeah, go quick. So each time, go ahead and just write, do this for me, everybody. Write A equals, underneath that write H equals, underneath that write K equals. And you're just going to write, I'm going to give you some examples, and you're just going to write down the values of A, H, and K for a bunch of different examples. Okay, so how about this one right here? Everybody take a second and look at this. I'm just going to go around the room, group to group. Group number 1, what's A?
1/2.
Is it 1/2?
Or negative 1.
Negative 1/2, there you go. Group 2, what's H? Negative 1, good job. What's group 3, what's K? 2, excellent, good job. Everybody give me thumbs, does that make sense? Okay, erase those numbers and try another one. Wait till he gets back. Yeah. Who went? Can't remember who went. Somebody went. No, somebody just went. I can't remember who it was, but somebody just did. Oh, the pass. Go ahead, then that's fine. Take the pass. Okay, everybody look. Okay. All right, so we were on group 4. I'm going to start with H. I'm going to start in the middle here. What's H? Negative 3. Good job. H is negative 3. Give me thumbs on that. Everybody got that? Okay, what is K? Next group. Negative 4. Okay, now I'm going to give you a hint on A real quick. I want you guys, we're just do a warm-up one. I'm going to write down the equation of a line here. Oh, boy, that's... Okay, everybody, what form is that line written in? Slope-intercept form, okay. So tell me, what is the slope equal to? 1, what's the y-intercept equal to? 4. Okay, good. So now, what's the value of A? 1, exactly. Not 0, it's 1, isn't it? Whoops. Right? And what's the moral of the story? Anytime that a number that's being multiplied, anytime a number that's being multiplied is invisible, what is it really? 1. It's a 1. Good. Okay. Give me thumbs on that one. We good? Okay. Erase those numbers and try this one. All right, here we go. Let's see. First group. Oh, I'll give you a second, Jaylee. There you go. Okay, what's A equal to? Yeah, what is it? -1. There you go. And how come? Because that's a -1, isn't it? Okay, next group. What is H? 0. Okay, there's an important lesson there. Anytime a number that's being added or subtracted is invisible, what is it? 0. Okay, there you go. And what's K? -5. One more. Try that one. All right. Okay, over here. You guys, what's A? 2. Correct. What is H? 6. What is K? 0. Because nothing is being added at the end. Give me thumbs. Erase the boards. Grab a seat. Okay, last thing, well, not the last thing, but before we jump into actually graphing these, I just want to show you something. I'm going to show you, you know some stuff you don't even know that you know yet. So, like if I wanted to graph this function, I wouldn't really know how because I don't know how to graph the parent function. You might, but what is the parent function?
That's just slope, so that'd be y equals.
Okay, but yeah, but what's the, yeah, what kind of function is this? What's the parent function? If I erased all the numbers, what would I be left with?
2.
Yeah, x squared, right? Everybody agree? If I erased all of the numbers, I would just be left with an x squared graph. So we don't know this yet, but we might know this. The graph of x squared is just a parabola, right? Okay, so what would we do to that? Well, what's the value of A?
-1/3.
Okay, so what's that doing to our graph, to our U-shaped parabola? The negative makes it go down, and the 1/3 does what? It's going to cut it 1/3. It's going to compress it, isn't it? It's going to squeeze it vertically. What's H? -1. And what's K? What's K? Nothing, meaning 0. Yeah. So that tells us that the vertex of that parabola would be at -1, 0, right? So we know how to graph this thing. Even though we haven't graphed parabolas yet, that gives us a roadmap to graphing this parabola, right? And we could do it with other weird functions too. What about that one? Like that's a totally different kind of function. Peek at that for a second and see if you can tell me what the parent graph is. Hey, what's up? Oh, here, let me get back to you in a sec. Okay, bye. So what kind of graph is this? What kind of function? It's a square root. If I erase all the numbers, I'm just left with the square root of x, aren't I? Right? So what's that look like? Well, it just starts at a point and then it kind of just flattens out with time. So we could start with that graph and we could tweak it in this way. What's A? 1. So we didn't stretch it vertically at all. What's H? -4. So we slid it to the left 4. And what's K? So we slid it down 7 and we could graph it. See my point? All right, so let's skip up Let's just try a couple of these. So what about one like this? We'll just go through some examples. So f of x equals 1/2 times the absolute value of x. Okay, you tell me real quick, what is a? 1/2. Okay, what is, I want to know now, what are h and k? 0 and 0. Okay, so now, when we want to graph this thing, all we really need is the vertex and one other point. So that's where the t-table comes in. So we know that the vertex has coordinates 0, 0, so it goes right there. We need one other point though, and that's when we use a t-table. So we want to input another x value that's close to the vertex. So we could plug in 1, for example. What would happen if we plugged in 1? If I plugged in 1 for x, let's see what we get. If I plug 1 into my function, f of 1 would just equal 1/2 times the absolute value of 1. Well, what's the absolute value of 1? 1 times 1/2? Yeah, it's just 1/2, right? So I would get the point x equals 1, y equals 1/2. That's not a super convenient point. Over 1 and up 1/2. So what else could we do maybe? Ah, okay. Yeah, what if we tried something like 2? What if I plug 2 into my graph? Then I get 1/2 times the absolute value of 2, which gives me what? 1. Okay, so that means if I plugged a 2 in, I got 1 out, and so I've got the ordered pair over 2 and up 1. So I started at my vertex, and that defined the right leg of my v. Everybody see that? The left leg I get for free because absolute value functions, like parabolas, like the x squared functions, they have this really nice feature where they have folding symmetry about the axis of symmetry. All that is the vertical line through the vertex. I can take any point on one side of that line and automatically just reflect it over to the other side and get another point for free. Okay? And there's my v. Now, how do we do this? Let me demonstrate using the graphing tool to do this once, because you're going to be doing this on the assignment. So let's try one of these. Oh, man. Okay, here it is. Okay, so one like this. Here's a problem on the assignment. So we're trying to graph the function absolute value of x plus 3 plus 6. So what's the value of a, everybody? 1. What's the value of h? -3. And what's the value of k?
6.
Okay, so then the vertex has coordinates -3, 6, correct? Okay, so let's graph this. I'll use the graphing tool, and in the graphing tool, which one of those buttons do I want to pick to graph an absolute value graph?
The V one?
Yeah, the V one. And if I hover over it, even says absolute value tool. So I pick that one, and the vertex you told me is at -3, +6. So I just go over to the point -3, 6 right there, and I make a point. Now I just need one other point, because that's all the tool wants me to do, is define where the vertex is first, and then pick one other point that's on one of the legs. So we need to plug in some other value of x into our function. What would be an easy one to plug in? I could plug in 1. How about 0? If I let x equal 0, then I get the absolute value of 0 plus 3. That's just 3, right? Absolute value of 3 is 3. 3 plus 6 is 9. Agreed? So I could just go to the point My other point, I could just go to the point 0, 9, which is right there. And look, it automatically reflects it and creates the other leg for me for free. And I just save that, and we got it. Piece of cake. Okay? Give me thumbs on that. Does that make sense? Okay? So let's practice just a couple more of these together, and then I'll turn you loose. So let's try this one. Okay, stare at that for a second. So can anybody tell me from looking at this here, what are the values of h and k? What's h? Negative 4. And what's k?
3.
There you go. All right, so there's one point already that we have the vertex has coordinates negative 4, 3. So negative 4, positive 3 is right there. I need a t-table and one other point. So what's another value of x I could plug in here? 0. Why not 0? Okay, so if we plug 0 in for x, what am I going to get? So f of 0 is going to give me negative 0 plus absolute value of 0 plus 4 plus 3. What's the absolute value of 0 plus 4? 4. So that gives me negative 4 plus 3. Well, negative 4 plus 3 is what? Negative 1. So I get the point 0, negative 1. And all I would have to do now is just start at my vertex, and that gives me one leg. The other leg I get for free. I would just take this point right here, and it's what, 4 over from the axis. So I'm just going to go 4 to the left. So over to there. There's my other leg, and I got it. Okay? Give me thumbs. Okay? One more. How about that guy? What's A? 3. What's H?
5.
What's K?
6.
Okay. So then we already know that our vertex has what coordinates?
5 and negative 6.
5, negative 6. So over 5, down 6. Okay, I just need one other point, so pick an x value. I could plug in 0. We got to be a little bit careful though. If I get too far away from my x coordinate of my vertex, sometimes the numbers get pretty big. Like if I plug, see what I'm saying? Like we want to probably stay pretty close to the vertex. If I plug in 0 in this case, that's pretty far away. I end up getting, it's going to work, but we just got to be careful, right? Like normally you'd want to pick numbers closer to 5. But 0 actually works though, so we'll try it. We can always try it. If I plug 0 in, f of 0 is going to give me 3 times absolute value of 0 minus 5 is absolute value of negative 5, right? Minus 6. What's the absolute value of negative 5? 5. So that gives me 3 times 5 minus 6. What is that? What's 3 times 5 minus 6? 9, yeah. Oops, that's not 0. So I get the point 0, 9, so clear up there. Okay, and I could just do that on my graphing tool. I would just pick that as my other point, and it would automatically create both legs. Okay, you want to do one more, or you think? How about this one? What's the value of A, everybody? What is it? Negative 2. So predict what this is going to do to the V before we even start this thing. The negative is going to make it go down, and what's the 2 going to do? It's going to stretch it. So it's going to be stretched vertically and reflected, all right? So that's what we should expect to happen. What's the value of H? Oops. Negative 6. What's the value of K? There you go, all right? So we already know our vertex. Here, let's put this, give ourselves a little more room, put that up here. So we already know that our vertex has coordinates -6, -3. So -6, -3 is right there. We need one other point. What would be a good value to pick for x? -5. Why not -5? Okay. So if I plug -5 in, what do I get? Plug -5 in for my input, and I get -2 times the absolute value of -5 plus 6 minus 3. What's -5 plus 6? 1. What's the absolute value of 1? So then all this stuff right there, doesn't that just, well, what's that become? -2. -2 times 1 is just -2. What's -2 minus 3? -5. Okay, so then -5 is what goes there. So now I've got a point at -5, -5, and I've got it, right? Here's my axis of symmetry. There's the right leg, so that must be the left leg. Okay, give me thumbs. Does that all make sense? Go to work. You got this. How much time do we have? Do we have any? 4 minutes? Okay, well, relax then. We're done. Tomorrow I'm going to give you a work day for this assignment. I'll put the review up. I think we'll review on Thursday and test on Friday. Sound good? Put the review assignment up. I think this is not really a very difficult test. Compared to the last one, I think this is easier. There's not much going on here, right? We're graphing lines. We're finding inputs and outputs of functions. We'll review that stuff. And then we've got this and graphing linear inequalities in two variables. I think you'll find this one isn't too bad.